All right, so we're going to talk about the dot convention now, which I've been kind of mentioning but haven't really talked about just yet. The dot convention is very important. So when you see transformers or you see coupled inductors in circuits, most of the time you're going to see the two inductors. You're going to see the two inductors. My hand is like falling off the screen here, so I'm having a hard time drawing something that looks reasonable. And then you're going to see some dots. You might see the dots here. You might see the dots here. You might see both dots down here. Very unlikely. And you could see this combination. It really just depends on the circuit, depends on the setup, depends on the topology. But nonetheless, we need to understand what these dots mean and what they're telling us. And the purpose of these dots is to tell us which way the coil was wound. Because if you remember, if I have a wire that's got current flowing through it in this direction, that means that I have a magnetic field or magnetic flux lines going around the coil, coming basically out from the backside and wrapping around like this. Okay, that is if I have current flowing in that direction. If I have current flowing in the opposite direction, so let's draw a different wire here, current flowing this way, that would result in the other direction for the magnetic field lines, okay? So it does matter which way the current is flowing. And if I draw the coil as being wound in this direction, basically the windings are going around the coil. I guess in this case it would be counterclockwise. It's kind of hard to tell. But winding it that way versus winding it this way makes a difference, because if you notice, in this case, the current, let's pretend that, or not, we're not going to pretend, but this is the part of the coil that's closest to me if I was looking at this in 3 dimensions, right? It's basically going close to me, farther away from me, closer to me, farther away from me, closer to me, etc. So the part that's closer to me has the current flowing in this direction, right? And that means that the magnetic field lines would be coming down into the coil from the outside, okay? So I would be looking at magnetic field lines that look like this. They're going upward on the outside, pointing from north to south like this, and then down through the coil. On the other hand, in this circuit, let's see what we've got here. So this time I'm assuming that I wound it such that the closer part to me is this one, right? Both of these cases I'm assuming the current's flowing down into the coil and then down back out of the coil. But in this case, I'm assuming that this is the closer part of the coil to me, and then it goes further from me, and then it gets closer to me, further from me, closer to me, further from me. This is really difficult to do in 2 dimensions, but basically you get the gist. This part of the coil has current flowing in this direction. So these 2 inductors look essentially the same, but the difference here is that if I do the right-hand rule, now my flux lines point up and out of the circuit and then go downward like this, which is not the same thing as what I've drawn on the left. You can see here that on the outside, oops, I screwed this up. This one goes like this. You can see that on the left-hand side, the parts of the magnetic flux lines that are outside the coil are pointing upward, right? And on the other coil, they're pointing downward. And that makes a huge difference, because in my circuit, if I have an induced current or an induced voltage, I need to be able to keep track of whether that voltage is positive from top to bottom, or is it positive from bottom to top? Is current that's induced going to flow down through my coil, or is it going to flow up through my coil? All these things matter, and the dot convention is how we take care of that, okay? So let me kind of blow these images up, because I kind of took a lot longer on this than I thought I would. And we'll just make this a slide. And then in the next slide, in the next video, we'll go over the next couple slides. I basically made a reference from the textbook. I took this chart from the textbook showing how we can verify that we understand the dot convention here. I'll talk about this one in the next slide, and then I'll do a little bit of an example to just show you how I understand and how I use the dot convention for reference when I'm solving these circuits. And then I think from there we'll be good to go and start solving some circuits. So let's get right into it. If you have any questions, obviously feel free to let me know. The important takeaway from this slide and this video here is that we're going to see these dots on these circuits, and we just need to understand that the dots basically tell us the polarity of the voltage and the current that we induce in the coil that's in proximity to the one with the current. So again, if the dot is here, that means that the voltage polarity is going to be one way. If I were to draw the dot somewhere else, the voltage polarity would be a different way. And so that's going to play into how we write our KVL loops, how we solve for the currents, etc. in these circuits. All right, so this does tend to be confusing. I said this already. It does tend to be confusing for people. It was really confusing for me when I first learned. So don't feel bad if this is confusing to you. It is a confusing topic, but I'm confident that we can get it figured out. So I'm going to go ahead and end this video, and in the next video, we'll kind of wrap up talking about the dot convention with a couple more slides.